Okay, Assalamualaikum and greeting to all. Okay, for today we will discuss chapter 6. Okay, chapter 6 is about circular motion. Okay, another types of motion that we will learn in this semester. Okay, so under circular motion, there are some cases that we will discuss that will be shown in our PSPM. Okay, so this is an overview. So what is in this chapter? Okay, so chapter 6 is about circular motion. So the first part for this video, we will discuss about uniform circular motion. So what is uniform circular motion and the parameters that appear in the circular motion. Okay, and the second part of chapter 6, we will discuss the centripetal force. So in this subtopic, so most of the question in PSPM come from this subtopic, which is under centripetal force. Okay, so first, okay, so this is the first part. Okay, this is the first part in chapter 6 that we will discuss. Okay, the first part. Okay, this is the part 1. Okay, and this is the part 2. Okay, so the part 1 is uniform circular motion. Okay, so what is uniform circular motion? So uniform circular motion, okay, is a motion in a cycle. Okay, motion in a cycle. Okay, at a constant speed. Okay, at constant. Okay, at constant speed. So in this definition, the most important thing is the constant speed, not velocity, but constant speed. So definition for circular motion is a body in a motion in a circular motion at a constant speed. Okay, that's a definition for circular motion. Okay, so under circular motion, the main that we want to look at is the linear velocity or the tangential velocity v. Okay, that appear in this subtopic. So in this situation, figure 6 here show a path of the circular path, okay, that the body will travel. Okay, there are 3 positions that I take. Okay, the first position here. Okay, so here there are r means the radius or the distance from the center of the rotation to the object or to the body. Okay, and from the body there, so the blue arrow here, this is represent the linear or tangential velocity. Why we call it linear or tangential velocity? Because the angle between V and R here are perpendicular or 90 degrees. So that's why we know. So this velocity is known as tangential velocity. Okay. So there are second position that I take. Okay, in the second quadrant. Okay, and also tangential to the radius. Okay, and the third position here at the bottom. Okay, also tangential to the radius. So okay, so in this situation, the most important thing that we look at here, the speed. Okay, so the first one here. Okay, so the first one we look at the speed. Okay, the speed or the magnitude. Okay, the magnitude of the velocity is always constant. Okay, it's a constant. Okay, so for example here v equals to 2 meter per second. So in this situation also v, the magnitude here also 2 meter per second, and the situation here v here also equals to 2 meter per second in its magnitude or its speed. So at constant speed. That's why this situation is known as uniform circular motion. That's our first point that appear in this figure. Okay, the second one, we look at the direction. The direction. Okay, so the direction of V we look at is keep on changing. Okay, the first situation is going upward, up there. Okay, the second situation down here, X and Y, and the last position here we look at it's moving to the left, to the right. So the direction of the V is changing. It keep on changing. Okay. So as a result, the third point, okay, or the third point or the main point here, okay, so we have learned in chapter 2, okay, in chapter 2 kinematics of linear motion. So the change of velocity, the rate of change of velocity, that will appear acceleration. So in this situation, so the velocity is a vector quantity, means either the magnitude or direction change. As a result, acceleration will appear. So in this situation, the magnitude is constant, but the direction is changing. So as a result, there are acceleration will appear. So as a result, okay, acceleration will appear or occur. Okay, so the acceleration will occur. So this acceleration is known as AC, or known as centripetal. Okay, centripetal acceleration. Okay, centripetal acceleration. So for the centripetal acceleration, so the direction of the centripetal acceleration is always toward the center of rotation. So the AC, the direction of AC, direction of AC always toward the center of the rotation. Okay, always toward the center of rotation. So this is the result when the direction of velocity change, so the acceleration will appear. So this acceleration is known as a centripetal acceleration. Okay, the direction of centripetal acceleration is always toward the center of rotation. Okay, and the next one is, okay, so this is a parameters that appear in circular motion. The first parameter that we want to look at is, the first one is period. The symbol is capital T. So what is period? So period is the time taken. Okay, it's a time taken. Okay, time taken to complete one revolution or one rotation or one cycle. So time taken to complete one cycle or one rotation. That's known as period. Okay, so unit for period is second. Okay. The next parameter that we look at is a frequency. The symbol is small f. Okay, so frequency is a number of revolution. Please do not be confused with the period. It's a number of revolution that complete in 1 second. So means how many cycle that body will make under one or in 1 second. So how many revolution or how many cycle or how many rotation that body can make in 1 second. That's known as frequency. So unit for frequency is hertz, SZ, or sometimes we use per second. Okay, so equation for the frequency is F equals to 1 over T according to the unit. So it's a 1 over T or 1 over period. Okay, so the next one we look at is the speed. Okay, the speed of a body. Okay, so based on formula in chapter 2, so the speed V is a distance travel over time. So the distance travel in a circular motion, okay, based on mathematics, so we can write, so the distance travel in a circle, so which is equals to 2 pi r. This is equals to 2 pi r, and time interval here of course is a t. Okay, so we get V equals to 2 pi r over t. So this is the formula, the first formula for the speed. Okay, formula for the speed. Okay, or the magnitude of the velocity, which is given by 2 pi r over t, or we can write V equals to 2 pi rf. So these are relationship between T and F here. Okay, so when the body move in circular motion, so another parameter that appear is known here is omega. Okay, it is known as omega. So omega here is known as angular velocity. Okay, it's an angular velocity. Okay, so angular velocity only appear when the object move in circular motion or rotating. Okay, so I repeat again. So angular velocity or omega here only appear when object move in circular path or moving in rotation, which is given by formula omega equals to 2 pi over t. Of course, this is very familiar to you. Okay, so omega equals to 2 pi over t. Again, we have t. So omega also can be write as 2 pi f. Okay, 2 pi f. Though in this section, when I relate with the velocity v, so omega also equals to v over r, or v equals to r omega. So this is another formula, or the third formula for the magnitude of the velocity of the speed for a body that moves in circular motion. Okay, continuation of chapter 6, part 2a. Okay, for 6.2, we'll learn about centripetal force. Okay, there are two subtopics in 6.2. Okay, which is first one is define centripetal acceleration. Second one, solve the problem related to the centripetal force for uniform circular motion cases. The first one is conical or pendulum. Second, horizontal circular motion. And the third one is vertical circular motion. Okay, include and backtrack. Okay, for the first one, for the centripetal or radial acceleration, here for centripetal acceleration, okay, we have looked at in the first part. Okay, the symbol for centripetal acceleration is AC or AR. Okay, which is the acceleration of an object move in circular path. The direction is toward the center of the circular path. Okay, whose the magnitude is equal to the square of the speed divided by radius. So given by formula AC equals to V square over R, or AC also equals to R omega square or V omega. So here's the diagram that representing the first tangential velocity, centripetal acceleration, and at the same time we have FC, which is represent centripetal force. Okay. So when we look at the direction of the centripetal acceleration, is always directed toward the center of rotation. Toward the center of rotation. Okay, and we look at FC and AC is both are perpendicular with a tangential velocity or linear velocity. Okay, in uniform circular motion, magnitude and the centripetal acceleration is always constant. So the magnitude of AC here, when look at here, is always constant. But in some situation, here the direction is basically based on the position. Okay, the direction of centripetal acceleration is continuously changed according to the position of an object around the circular path. For the centripetal force, okay, this is essential in this second part. The net force on a body cause it move in circular path of the magnitude given by Fc equals to mv square over r, or mr omega square, or mv omega. So this is the general formula for the net force of the centripetal force, which is mv square over r. So from here, okay, so Fc equals to mv square r. Okay, we can relate it to the Newton's second law. Okay, for Newton's second law, which is F net equals to ma. So this is that we learned in chapter 4 of the linear motion. So when we change into circular motion, so F net here will be equals to mac. So ac here that represent the centripetal acceleration. So direction of the fc here, centripetal force, is same direction with ac. Okay, so from here, as we learn m, so AC equals to V square over R. So that's why we'll get FC equals to m V square over R. So the centripetal force suddenly stop. If the centripetal force is suddenly stopped at a body in the circular motion, so the body will fly off in the straight line with a constant tangential linear. Okay, this is an example. Okay, for example, when the body stop applying centripetal force, so what happened to the body? So the body will move in the straight line, which is cause that Fc equals to 0. And then at the same time also LAC or centripetal acceleration also equals to 0. So in uniform circular motion, the net force on the system is the centripetal force. Okay, in uniform circular motion, the net force on the system is centripetal force, which is equals to mv square over r. So the work done by the centripetal force is 0, but the kinetic energy of the body is not 0. It's given by formula half m r square omega square. Thank you. Okay, chapter 6, part 2b. This is example of the uniform circular motion. Okay, so for this subtopic, at the end of the chapter, students should be able to first to relate the centripetal force for uniform circular motion in case conical of pendulum, horizontal circular motion, and vertical circular motion. Okay, so in this case, okay, so generally we want to find out what types of force that contribute to the centripetal force, which is equals to Fc equals to mv square over r. So what type of force that contribute to Fc? For different cases, will give you different types of force that you need to fulfill in this box. Okay, so the first one. Okay, the first one is conical of pendulum. Okay, so conical of pendulum. So why known as conical of pendulum? When this pendulum bob is moving, so it's just look like a cone. Okay, so in this side there are a free body diagram that I draw to show the situation of the pendulum bob. So from here, so this is tension. Okay, tension in the string here, the blue arrow here, tension in the string, and then we have mg or weight of the pendulum bob. So the centripetal acceleration is toward the center of rotation. So this is the center of rotation of the pendulum bob. Okay, so the next step that we need to fulfill is what is in the box. Okay, what is in the box, which is contribute to mv square over r or equals to fc. Okay, so when we look at here, so the component x, okay, the component x is contribute to fc, which is equals to t sine theta. Okay, t sine theta equals to mv square over r. So this is the step of solution that you need to find out to solve the case in conical of pendulum. The next case, number 2, is motion around the curve on the flat or unbent track for a car, motorcycle, and bicycle. So this real situation is like in a roundabout. Okay, roundabout. So a car at the roundabout or at the corner. Okay, so this is my diagram. Okay, so centripetal acceleration is always toward the center of rotation. Okay, toward the center of rotation, the centripetal acceleration. Then, so my free body diagram is wake of the car going downward. Normal of the car, because the car have contact with the road, is upward, perpendicular to the surface of the road. And the friction, okay, the friction force that prevent the car from skidding outside the road. So direction of frictional force is toward the center of rotation. Okay, the frictional of the tire of the car is toward the center of rotation. So same things goes to here. So we need to fulfill what is the types of force that contribute to FC. Okay, so in these cases, component X, okay, component X, Fx equals to mv square over r, because the direction of AC is on component X. So in this situation, only frictional force is equals to mv square over r, okay, which is equals to mu n equals to mv square over r, or mu mg equals to mv square over r, which is here in this situation mg. Okay, we refer to the component y, which is equals to n, normal. Okay, so in these cases, so this we need to find out the maximum velocity of the car just before the car skidding, which is equals to set mu naught mu rg, set mu rg. This is for second case. Okay, the third case is for horizontal circular motion. Okay, horizontal circle or horizontal circular motion. So the pendulum bob made a horizontal circular motion. Okay, so my free body diagram here. Okay, so I have an AC. Okay, so this is my body, the tension from here. So mg downward tension, and this is here is the center of rotation. Okay, so from here, when a body have a contact with the surface, so we'll have a normal reaction force is going upward. So in this situation, T and AC are in the same direction, so means here component X, still component X, Fx equals to Fc equals to MAC. So here T, or tension in the string, is contribute to Fc, which is equals to MAC. And the last case in this subtopic is about vertical circle. Okay, it's about vertical circle. So there are three situations that we need to consider. Okay, point A, point B, and point C here at point C. So at point C here is a same concept for horizontal circular motion. Okay, so now we just focus to at point A and at point B, at the lowest point and the highest point. So first we look at point A, at the lowest point. So this is my diagram. Okay, first this is the center of rotation. The centripetal acceleration is always toward the center of rotation. The car is at the bottom. So what happened to the car? So the car have a wake is downward. Normal reaction force is upward. Okay. So in this situation, contribution to FC is mg and normal reaction force, but both are in opposite direction. So in this case, we are using the Newton's second law. So we get NA minus mg equals to mv squared over r. Why NA minus mg? Because mg is in opposite direction with AC. So of course mg will become a negative. So this is the solution or step of solution for, or equation for the body at the lowest point in vertical circular motion. At point B, or at the highest point, okay, at the highest point, at the highest point, so the center of rotation still here, okay, AC toward the center of rotation. So what happened to our free body diagram or diagram of forces for our car? So mg downward is always downward, and we have change in direction of normal reaction force upward to downward due to the contact here. So in this situation, we have both mg and n are in the same direction with AC. So an equation that we can write down is n at point B, normal force at point B, plus mg equals to mv squared over r. Okay, that's all. Thank you very much.